So now we're at the third question of the paper. Determine the coefficient of x to the fourth power in the binomial expansion of 1 minus 2x over 1 plus 3x all square. So let's expand. So we have 1 minus 2x. So I'm going to rewrite bring up the denominator in the numerator there. So based on the laws of indices, the sign of the power will change. So it was positive 2, it's now negative 2. So this is what we need to expand. So what we have is 1 minus 2x times 1 plus 3x to the power of minus 2. Now what you'll notice is that we're only asked to find the coefficient of x to the fourth power. So we don't need to write all the terms. We don't need to write all the terms. Alright, so we know that. So we just need maybe the term in, of course, definitely the x to the fourth power. We also need the term with x cubed, because when you expand, when you multiply by x, the 2x by x cubed, you'll end up with a term with x to the fourth power. So really we just need two terms. The one with x to the fourth power and the one with x to the third power. So let's just expand separately 1 plus 3x to the power minus 2. Now, we know that 1 plus x, the formula there, 1 plus x to the power n is 1 plus nx plus n times n minus 1 x squared over 2 factorial plus n times n minus 1 times n minus 2 x cubed over 3 factorial plus n times n minus 1 times n minus 2 n minus 3 x to the fourth power over 4 factorial. So we only need this term and this term. Let's work on those now. So applying this formula here to 1 plus 3x to the minus 2, n would be the minus 2, and of course in this case it's x, but here's actually 3x. Alright, so where we have x here in the formula, we'll actually replace it with 3x and replace n with minus 2. So let's work on this term. Alright, so n, we'll have n to be minus 2, so that's minus 2 times n minus 1, that's minus 2 minus 1, that's minus 3, n minus 2, that's minus 2 minus 2, that's minus 4, x cubed over 3 factorial. Now 3 factorial is 3 times 2 times 1. So 3 factorial is actually 3 times 2 times 1, which is actually 6. Alright? Plus, and let's put, well, I made an error here. It's actually, instead of x cubed, we're using 3x. So it's actually 3x cubed. Very important. Alright, so replace x with, match the formula, 3x cubed. Alright, next term, with the x to the fourth power, again n is minus 2 times n minus 2 minus 1, that's minus 3, times minus 2 minus 2, that's minus 4, and minus 2 minus 3, that's minus 5, x to the fourth power, and we're replacing x with 3x, so it's actually 3x to the fourth power, all over 4 factorial, and 4 factorial, that's 4 times 3 times 2 times 1. So 4 factorial is actually 24. So I don't need this anymore. Let me just. So what we have here is 1 minus 2x. And then 1 plus 3x to the minus 2, we only take in two terms, as we discussed earlier. So the minus 2 minus 3, that's positive 6. Cancel with the 6 below here. So what we have here is actually minus 4 times 3 cube. So it's actually minus 4 times 3 cube x cube. So 3 cube is 27. So it's actually minus 4 times 27. That gives me negative 108. So this is negative 108 x cube. So we square both the cube, both the 3 and the x. That's 27 times the negative 4. Alright. Come over to here now. Here we have minus 2 times minus 3 times minus 4. These cancel with 4 times 3 times 2 down here. But of course I'll still have a negative, because this is negative 24 over positive 24. So I'll left with a negative 1. So the negative, so actually this is actually positive 5 now we have here. So it's positive 5, double negative, times 3 to the power of 4. Now 3 to the power of 4, that's 81. So it's 5 times 81. And that gives me 405 x to the power of 4. And therefore now, let's expand now to get the x to the 4th power. So if I'm expanding, when I'm expanding, I'm just interested in the one that would give me x to the power of 4. This 1 times the 405, so this will be 405 x to the power of 4. And then when I'm expanding, the minus 2x times the minus 108, that will give me positive 216 x to the power of 4. Alright, so I have two terms there with x to the power of 4. So when I add them, 405 plus 216, I'm getting 405 plus 216. I'm getting 621. So this is 621 x to the 4th power. So in answering the question, the coefficient, so therefore the coefficient is 621. Let's move on. Part B, show that if the series 1 plus 7 over 3x minus 5, and if you notice, the terms are increasing, the power is increasing by 1 each time. So right away we can pick up that this is an it's a geometric progression. It's actually a GP. And if you'll notice, A is 1, first term there is 1. So GP with the first term there is 1. And the common ratio R, if you notice, is 7 over 3x minus 5. So you'll notice power is increasing by 1 each time, which means that to get the term, the next term in the sequence, you are always multiplying by 7 over 3x minus 5. So the formula of a sum to infinity, so the sum to infinity formula is equal to A over sum to infinity, A over 1 minus R. And we know the value of A is equal to 1 divided by, we'll write it like this, so it's 1, which is A, divided by 1 minus R. And what is R? R is 7 over 3x minus 5. So what we can do is in the bracket, we can put everything under one common denominator. So we can rewrite 1, right? We can rewrite 1 as 3x minus 5 over itself, same as 1. So we conveniently do that to ensure we have a common denominator. And this is 7 over 3x minus 5. So since we have a common denominator now, we can put the numerators together. So this is 1 divided by the common denominator, 3x minus 5 minus 7, right? So this is 1, and we can times and reciprocate, so flip, so the 3x minus 5 is now the numerator, and in the denominator is 3x minus 5 minus 7. So it's 3x. And then minus 5 minus 7, that's minus 12, right? So that gives us 3x minus 5 over 3x minus 12. And I believe that's what we're asked to show. The 3x minus 5 over 3x minus 12. Let's move on to question part C. Use mathematical induction to prove that the nth derivative of e to the x times sine x equal 2 to the n over 2 times e to the x sine x plus n pi over 4. And we're given some identities that we can use. Sine x plus cos x is root 2 sine x plus pi over 4. And we're asked to, and we're also told that this. Alright, so it's a proof by induction, and proof by induction is follows 3 basic steps. So step 1. Alright, let's do step 1. So step 1, show it's true. So for step 1, so we're going to show true for n equal to 1. Alright, so we're going to show true, show it's true for n is equal to 1. So if n is equal to 1, then dn would be d1, so it's the first derivative. Alright, so if n is equal to 1, then we'll find derivative of e to the x sine x over dxn, but we're using n to be 1, so it's just dx. Alright, x is the same thing as x to the power 1. So let's differentiate this and see if we get whatever we have here. So if we differentiate this, we'll get, so of course we differentiate e to the x times sine x, that will be a product rule. So differentiate e to the x, we'll get back e to the x, and we'll leave the sine x alone. Plus, we're alternating now, so this time now we're keeping the e to the x, and differentiate sine x, we end up with cos x. And of course, notice we have a common factor, e to the x, so we can factor out e to the x, and we're left with sine x plus cos x. And notice we're told, we're given the identity for sine x plus cos x. We're told that sine x plus cos x is actually root 2 sine x plus pi over 4. And since it's root 2, let me put the root 2. This is commutative, multiplication commutative. So let me put the root 2 in front of the e to the x. Alright, so let me put the root 2 here, and e to the x after. Now, the question is this derivative, the first derivative, the same as this expression here when n is 1? Alright, notice what we have here when n is 1. When n is 1, then what the formula will give us is d1, d differential derivative, first derivative e to the x sine x. Let's check what the formula reveal when n is 1. If n is 1, this will be 2 to the half, 2 to the power 1 over 2. Now 1 over 2 is the same thing as root 2. 2 to the 1 over 2 is the same as root 2. So this will be root 2 e to the x sine x plus, if n is 1, then n pi will be 1 pi. So pi over 4. Notice we get the same thing as when we took the first derivative. Both are the same. So therefore, true when n is 1. So the formula works when n is 1. Alright. Let's go to step 2. Step 2 is about, so we assume true for n equal to k. Alright, so again, this formula we're simply going to replace the n with k. Alright, so step 2 is a very basic step. So rewrite the formula, except now we replace n with k, where k is some ordinary arbitrary constant. Alright, so dk e to the so therefore dk over dx k, and it's e to the x sine x is equal to, I'll go back to it, is equal to, so we write back everything except we're replacing now n with k. So 2 to the power of k over 2, 2 to the power of k over 2 e to the x sine x plus k times pi over 4. So all we did is rewrite the formula replacing n with k. Now step 3 is proven true for n equal to k plus 1. So step 3, alright, let me do step 3 down here. So step 3, we're going to show true for n equal to k plus 1. And if you notice, the question also told us that differentiating the k plus 1 derivative is equal to this. We get the k plus 1 derivative by differentiating the k derivative. Alright, so let me just restate this. Alright, dk plus 1 f of x. So the k, so let's restate it. So d k plus 1 to f of x. And remember f of x, what f of x was? F of x was e to the x sine x. So d e to the x sine x, that was what f of x was, right? Times over dx to k plus 1. So we are told that this is equal to the derivative of the kth derivative. And what's the kth derivative? So d k f of x, and f of x, we know, just going to put f of x was in this case e to the x sine x over dxk. So this is saying that we get the k plus 1 derivative by differentiating the kth derivative. In other words, you get the 4th derivative by differentiating the 3rd derivative, and so on. You get the 10th derivative by differentiating the 9th derivative, and so on. So, alright, so let's do this proof. Now, if you recall, we actually know the kth derivative, alright? The kth derivative was in the second step. Let's go back to the second step. The kth derivative, here's the kth derivative. Alright? So this is what we need to differentiate. Alright, so differentiating this, of course, again, we'll be using this is the kth derivative, so to get the k plus 1 derivative, we'll differentiate this. Alright, so of course it would be a product rule situation here, right? So let's differentiate the e to the x, 2k over 2 to the power k over 2, which is a constant, e to the x. So, alright, so differentiate that. We'll end up back with 2 to the power of k over 2, e to the x. We'll end up back with 2, let me write it here so we can look at it while we're doing it. Okay, so this was a k derivative, and this is what we're differentiating using the product rule. Alright, so the product rule differentiate this term first, differentiate e to the x, you still get back e to the x. And 2 to the power of k over 2 is a constant, so we still get back that, alright? 2 to the power of k over 2, e to the x sine x plus k pi over 4 plus, and we're going to product rule, so this time now we're going to restate, so we're going to put back this now and then differentiate the sign term. So we put back 2 to the power of k over 2 e to the x. And now this one we want to differentiate sine. But differentiating sine, we differentiate what's in the bracket with respect to x. We'll get 1. So 1 times that won't change anything. And sine will turn to cos. And the bracket will remain as it is. So what we could do in a common factor there, notice we have a common factor there, 2 to the power k over 2 e to the x. So this is factor out 2 to the power of k over 2 e to the x. Alright, and yes, well, yes, we end up with now in the bracket, we'll end up with now sine x plus k pi over 4 plus cos x plus k pi over 4. And then this is 2 to the power of k over 2 e to the x. Now you recall the summation of the sine plus cos. Let me just go back to that. The summation of the sine plus the cos. From up here, the summation of sine plus cos is actually root 2 x plus pi over 4. Alright, so if you interpret this formula here, put a root 2 outside, and then sine, and then whatever the angle is, you add pi over 4 to that. So let's do that. So root 2 sine x plus pi over 4. So this is actually root 2 sine x plus, so this is, in this case, all of this will be the x. Alright, x plus k pi over 4, this is the angle. Alright, plus pi over 4. Alright, so this will be like your x. Alright, same thing in both of the brackets there. We add pi over 4. So again, carefully look at how we interpret this. Alright, so sine x plus cos x is sine, and whatever the angle is, you put it back here and add pi over 4 to that. Alright, so that's where that is derived from. So what we end up with now is this becomes root 2 times 2 to the power k over 2. Now, root 2 is same thing as 2 to the power half. Alright, so if you add this 2, k over 2 plus 1 over 2, same denominator of 2. So it's actually k plus 1 over 2. Alright, k over 2 plus half, that's k plus 1 over 2. Alright, e to the x sine, in the bracket now, we'll have x plus, and then both of these have a common denominator of 4. So this is actually k pi plus pi. And if I factor out the pi, there, that's actually k plus 1. Alright? Now let's check if this corresponds with what the formula said that we should get. Based on the formula, we are given, where is it? So, alright. So let's replace n with k plus 1. Here we go. If you replace n with k plus 1, alright, so this would be d k plus 1 dx k plus 1 of the function e to the x sine x. They're saying what we should get is 2 to the k plus 1 over 2 e to the x sine, in bracket, x plus replacing n with k plus 1. This would be pi times k plus 1, or k plus 1 pi. So k plus 1 pi over 4. Let's see if that's what we had here. So let's check term by term. 2 to the k plus 1 e to the x. 2 to the k plus 1 over 2, sorry, e to the x. Alright, and sine x plus k plus 1 pi over 4. And of course, when we use the formula, we'll get the exact same thing. Alright, 2 to the formula. It replaces n with k plus 1, so it'll be 2 to the k plus 1 over 2. Sorry. Alright, e to the x. Sine x plus k plus 1 pi over 4. So we're getting the exact same thing. So therefore, true for n equal k plus 1. Hence, true for n, and usually for n greater than or equal to 1. Let's move on. Use the intermediate value theorem to prove that this function here has a root in the interval -2, -1.5. So we can let f of x be equal to whatever the equation is, x to the power of x to the 5th power minus 2x cubed plus x squared plus 2. Let's find f of -2. F of -2, we substitute in -2 for x, and then we end up with -2 to the 5th power minus 2 times -2 to the 3rd power plus -2 to the 2nd power plus 2, and I'm getting -10. That's the f to the power of -1.5. So it will be -1.5 to the 5th power plus -2 times -1.5 to the 3rd power plus -1.5 square plus 2 equal to 3.4. So notice the signs are different. So since f of -2 times f of -2 times f of -1.5. If you notice, one is -10 and one is positive 3.4. You multiply them, you'll actually get -34, which is less than 0. Alright, so since the product is less than 0, then therefore a root, by the intermediate value theorem, a root lies on the interval -2, -1.5. And part 2, use 2 iterations of the Newton-Raphson method with initial estimate x1 equal -1.5 to calculate a new estimate for the root in the same interval, -2, -1.5. Alright, so 2 iterations, so we're going to use the formula twice. So, you know, the formula says x to the power x subscript n plus 1 equal xn minus f of xn over f prime xn. Alright, so we know f of x. We need f prime x also. Let me just put f prime x here. F prime x would be the derivative of f of x. That's 5x to the power of 4 minus 6x squared. 5x to the power of 4 minus 6x squared plus 2x. That's what f prime x would be. We'll need that. So let's find, so we are given x1, let's find x2. So based on this thing here, if we let n be 1, then x2 would be x1 minus f of x1 over f prime x1. Alright, so we know x1 is negative 1.5 minus f of x1, so that's f of minus 1.5 over f prime minus 1.5. Alright, so f of negative 1.5 means we'll substitute negative 1.5 in the original function, and f prime of negative 1.5 means we'll substitute negative 1.5 in f prime, the derivative function. Alright, so when we'll do that, let's pass and do that, we'll get x2 equal to minus 1.5 over, so when I find f of negative 1.5, by substituting it into this function here, I'm ending up with minus 3.4, well, 3.4. Is it? 3.4. And when I plug it when I find f prime negative 1.5, by plugging negative 1.5 in f prime, I'm getting 8.8, and that works out to be negative 1.89. And then to find the second iteration, which would be x3, the third approximation, x3 is equal to x2, with the formula, minus f of x2 over f prime x2. So this would be, we know x2 to be negative 1.89. Minus, and this time now we'll be substituting, so x2 is negative 1.89. So we're substituting, so f of negative 1.89 over f prime of negative 1.89. So in the numerator, we plug negative 1.89 in f of x. In the denominator, we plug negative 1.89 in the derivative f prime. Alright, so x3, so we have negative 1.89. And when I substitute negative 1.89 in the original function, this function, I'm getting negative 5.04. Negative 5.04. And the double negative gives me actually a plus here. Right? And when I substitute negative 1.89 in the derivative f prime x, in the denominator, we're getting 38.59, and this calculated, this is actually negative 1.76. Part B, show that theta subscript n plus 1 is equal to sine inverse 2 over 8 minus theta square subscript n is a suitable iteration for the approximation of the roots of the equation cosec equal to 4 minus half theta square. Alright, so we know cosec is the reciprocal of sine, so we can rewrite cosec as 1 over sine theta equal to, and we can just have a common denominator here of 2, and of course 4 over 1. So to get a common denominator, 4 over 1 is the same thing as 8 over 2, right? Minus theta square over 2. So common denominator there. So if we reciprocate, well, reciprocate both sides, it means that sine theta, reciprocate the other side, is 2 over 8 minus theta square, and which means that theta would be equal to sine inverse over 8 minus theta square, and then we actually so the subscript. All right, so let me just put the subscript there. So theta n plus 1, as we are told, subscript n. Hence, using theta 1 as 0 as the first approximation, calculate the new estimate for the root of cosec, theta. So for the root of this equation here, so theta 1 is 0. So if theta 1 is 0, let's find theta 2. So to find theta 2, we can let n be 1, right? So we know theta 1 is 0. Alright, so using this formula here, if we let n be 1, then theta 2 would be sine inverse 2 over 8 minus, if n is 1, so here we'll let n be 1. Alright, so this would be theta square, theta 1 square. Now theta 1 is 0, so theta 1 square would be 0 square. Alright, if the subscript here is 1, 0, so that's 8 minus 0. So it's sine inverse 2 over 8, so that's sine inverse a quarter, and that's 0.25268. So 3 decimal places, so we try to work with more earlier on. Alright, so let's find another approximation. Let n be 2 this time. If n is 2, then then theta n plus 1 will be theta 2 plus 1. That's theta subscript 3. So that's sine inverse, using the formula here, would be 2 over 8 minus, replacing n with 2, theta square, theta subscript 2 square. Now theta subscript 2, theta subscript 2 we have as 0.25, so let me just put the extra here. So this is theta square subscript 2. Alright, but we know what the value of theta 2 subscript is. So this is equal to sine inverse 2 over 8 minus 0.25268 square, right? .25268 square, and that would give me, so theta 3 continuing would be sine inverse 0.252, so just in the bracket works out to be, alright, which is equal to 0.2545, which is not much different from this, right? So if I should use 2 decimal places, so you still get 0.25 again. Alright, so if I'm to have an approximation for theta, I would say theta is 0.255. And of course, I should have mentioned that we're assuming we're using radians. Alright, so for these you'll put your calculator in the radian mode. Part C. Determine the Maclaurin expansion for f of x equal to 1 plus x squared times cos x up and including the third non-zero term. So we know the Maclaurin's formula is f of x is equal to f of 0 plus x times f prime 0 plus x squared, second derivative evaluated at 0 over 2 factorial, and the pattern continues x cubed, third derivative evaluated at 0 over 3 factorial plus x to the power 4, fourth derivative evaluated at 0 over 4 factorial, and so on. X to the power n, f to the nth derivative over n factorial, and so on. So we know f of x. Let's find if we can find these values. So we know that f of x is equal to 1 plus x squared times cos x. Let's find f of 0. So f of 0, replace x with 0. That's 1 plus 0 squared, which is 1 in the bracket, times cos 0. And cos 0 is actually 1, right? So the first term in the series there would be f of 0. F of 0 is 1. Let's find f prime 0. To find f prime 0, we need f prime x, right? So f prime x, let's differentiate the function. And of course, we'll be using the product rule. So we differentiate the 1 plus x squared first. We get 2x. And we'll keep the cos x. Plus, alternating. Alright, this time now we're going to differentiate the cos x. Differentiate cos x is actually minus sign times, I will leave 1 plus x squared alone. So it's actually 1 plus x squared times minus sign. So minus, that will be a negative term. And then evaluate at 0. So f prime 0 would be, now x is 0, so this part will be 0. And this part would also be 0, because sine 0 is 0. So this will be 0, alright? So this term here, we rule it out, this would be a 0 term. Let's find the second derivative. So this time we're doing f, the second derivative. Now we want 3 non-zero terms. So f double prime. So again, for this piece product rule, so differentiate 2x. We'll get 2. We'll leave the cos x alone. And we'll alternate. This time we'll keep the 2x and differentiate cos x, we'll get negative sign. Alright, so that's negative sign. Let's come over here now. Differentiate negative 1 plus x squared. That's actually negative 2x times the sine x. Plus, we alternate. This time now we leave a negative 1 plus x squared alone. Alright, differentiate sine x. We get cos x. And then we evaluate at 0. So let's work out f second derivative, evaluate at 0. So replace this with 0. This will be 2 cos 0. That's 2. X is 0, so this will become 0. X is 0, this will become 0. And here, x is 0. This will become actually minus 1 times cos 0. But cos 0 is 1. So it's minus 1 times 1. So it's actually minus 1. So this will actually be just 1. So cos 0 is 1. And this is negative 1 times 1. So, let me just rewrite the second because I needed to fix it up to get the third derivative. So this is actually, this is actually 2 cos x. This is actually 2 cos x. It's actually minus 4x sin x. So this is actually minus 4x sin x. If I group these two middle terms, minus 1 plus x squared, just to fix it up for finding the third derivative, which we'll need. So the second derivative evaluated at 0 is 1. So this is a 0 term. So come to here. Alright, is actually 1, so is actually, this is 1. So it's x squared times 1, which is x squared, over 2 factorial, and 2 factorial is 2. Let's find the third derivative now. So to get a third derivative, we differentiate a second derivative, alright? So differentiate 2 cos x, we get negative 2 sin x. Alright, differentiate negative 4x sin x by applying the product rule. Alright, so differentiate negative 4x, we get negative 4. We'll leave the sin x alone. Differentiate sin x, we get cos x. So it's cos x times minus 4x, so it's minus 4x cos x. Alright, let's come here now. Differentiate negative 1 plus x squared. That's negative 2x times cos x, so product rule again. And then we're alternating now. So this time now, we're differentiating cos x. We're not with negative sin x. So negative times negative gives a plus term here. So this will be a plus term here. 1 plus x squared sin x. Alright. And if we just want to fix it up a little bit, this is actually negative 2 sin x, negative 4 sin x. That's actually negative 6 sin x. This is that group with that. That's negative 6x cos x plus 1 plus x squared sin x. And then I can evaluate at 0. Evaluate at 0. Sin 0, 0. X is 0, so this part will also be 0. Sin 0, 0. So all of this will be 0. Alright? Notice every other derivative will get 0 when we evaluate at 0. Alright, let's find the fourth derivative now. Fourth derivative. We'll get it by differentiating the third derivative. So differentiate this. We'll get negative 6 cos x. Differentiate this, of course, we'll be using product rule. So differentiate negative 6x, that's negative 6. Keep the cos x. Then we're alternating now. This time now we're going to differentiate the cos x. We'll get negative sin times negative 6x. So that's positive 6x sin x. And then the final term, differentiate 1 plus x squared. We'll get 2x, product rule again. We'll keep the sin x. And then we alternate, plus, we'll keep the 1 plus x squared. And differentiate sin x, we get cos x. And then we're going to evaluate at 0. So negative 6 cos 0 is 1. So negative cos 0, that's negative 6. Negative cos 0, that's also negative 6 again. This will be 0 because sin 0 is 0. Sin this is also 0 again. And here, if x is 0, the bracket will be 1. So it's plus, the bracket will be 1. So it's 1 cos 0. And cos 0 is 1. So plus 1. So what we have is actually minus 12 plus 1. That's minus 11. So the fourth derivative. So the third derivative was 0. So this was 0. These are 0. This was 0. And the fourth derivative, we'll get this now to be minus 11. So this would be minus 11 x to the fourth power over 4 factorial. And 4 factorial is 4 times 3 times 2 times 1. That's 4 times 3, 6. 6 times 2. 4 times 3, 12. 12 times 2, 24. So it will be 24. So these are the first 3 non-zero terms. 1, x squared over 2, 11x to the power of 4 over 24.